This is the third lecture of this week. Today's topic is traction. Okay, but before going into that, to start with, let us spend a couple of minutes time to revise whatever we have learned so far in the last two classes. Okay, what we have seen is that we define what is stress at a point. If we take a three-dimensional object which is subjected to some kind of external loading, and we discuss the stress is a response of the material to the external agitation. Okay. Now, if we take a point, say any point here, and if we want to represent the stress at this point, then we consider infinitesimal volume element around this point, and then the stresses are represented as this. Okay. So, this is essentially this volume element. So, this element is essentially this volume element. Okay. Now, stresses are represented on three planes of this volume element. In other three planes also we have the same plane, the same stresses. Whatever stress we have this on this plane, it's a mirror plane. We also have the similar stresses, which is not shown here for clarity. Okay. Then we also discussed that the stresses are stress at a point can be represented in various ways. This is the graphical representation or schematic representation of the stress, this one. And then this stress can be represented in a vector form like this, and then a tensor form like this. Now, if you see these, there are in total 9 components of stresses, but if you remember, we discussed because of the momentum balance, the off diagonal terms in the stress tensor, they are symmetric, the shear terms are symmetric. So, essentially we have 6 stress components. All the diagonal stresses are the normal stress on 3 planes, and the off diagonals are the shear stresses on different planes. Similarly, if I have if I represent the stress at a point in a 2-dimensional object, then the other components are 0, but here you make a star and you see there is nothing like 2-dimensional object, all object essentially in 3 dimension, but in some places we can idealize this object, idealize the material, idealize the structure as 2-dimensional structure. So, how we idealize that 3-dimensional object into 2D, there are depending on that we have some principle called plane stress, plane strain theory. We will discuss that in subsequent week, but to start with, do not consider this 2-dimensional representation of the stress. This is the general representation of the stress, and how to project this to this, how to project this 3D stress representation to 2D depending on the idealization. We will discuss that in the subsequent week. Okay. Now, we also discuss that whenever we represent a stress, for instance, this is the stress, it is always associated with certain coordinate axis. Okay. So, we choose a coordinate axis, and with respect to that coordinate axis, stresses are measured and stresses are represented. Now, if we have a point here, suppose this is the point, then at this point we can have at this point we can have, say, infinite number of coordinate axes, orthogonal coordinate axis. For instance, if we take any arbitrary coordinate, suppose this prime coordinate. Now, if we and the stresses are suppose stresses are represented with respect to prime coordinate as this sigma prime. OXYZ is the XYZ coordinate system, and OX dash Y dash Z dash is the prime coordinate system. So, this is the representation of stress with respect to this coordinate system, and this is the representation of stress with respect to this coordinate system. Now, these two representation can be related to each other through a transformation matrix, and this transformation matrix is Q. Now, Q is the transformation matrix. Okay. Q has a property, is an orthogonal matrix. It is an orthogonal orthogonal transformation. Now, that also we discussed, and then if you see, if I have to write this in indicial form, then this form becomes, this is the written in indicial form. So, if we know the stress at a point with respect to any coordinate axis, then if we can have infinite number of coordinate axes at the point, and then for any coordinate axis we can obtain the stress components by this transformation. Now, you see there are Now, there is next what we learn is we learn the concept of stress invariant. Now, you see, for instance, if I take an object, if I take suppose this is water body, and if I take some object here, okay, what would be the pressure on this object? You see, hydrostatic pressure on this object is, these are the pressure on this object, right? This is the pressure on this object, and this pressure do not have any this pressure does not have any specific direction. Any direction we take, this pressure is same. Therefore, if I take this coordinate, if I take this coordinate axis or this coordinate axis or any other coordinate axis, this pressure is going to be same. So, this pressure remains unchanged, do not vary even if we change the coordinate axis. So, this is called invariant. So, for instance, the energy. Now, energy of a system, if any coordinate system we take, energy at a point, energy and a small volume do not change, right. Now, the thing is, energy depends on the stress. So, energy can be expressed in terms of stresses. So, some combination of stress gives you energy, and therefore, some combination of stress must remain unchanged even if we change the coordinate axis. Some combination of stress gives me pressure, and therefore, since pressure is the, by definition it should be unchanged even if we change the coordinate system. So, some combination of these stress components should remain unchanged, and those combinations are called stress invariant. There are 3 stress invariants for a symmetric second order tensor here. So, we have the first invariant, which is the trace of this matrix or the tensor. Second invariant is the sum of the cofactor, and the third invariant is the determinant of sigma. That is also discussed. We have not discussed the physical interpretation of these invariants. We will discuss shortly towards the end of this week. Okay. Now, so this is we discussed in the last 2 classes. Now, let us understand what is traction. What is the topic today we are going to discuss. Now, first try to understand traction from what is the physical what is the physical meaning of traction. Then once we understand that, then we will see how the traction can be determined by knowing the stress at a point. Okay. Now, consider a 3-dimensional object here, and take any point, suppose take any cross section. Before that, if you recall your first year mechanics or structural analysis, if we have a any beam, say simply supported beam, consider simply supported beam, and which is subjected to some external loading, right. Now, if we draw the free body diagram of this beam, the free body diagram will be something like this. We have external loading on this, and then we have reactions at this end. This is a hinge support, that is why 2 reactions, and the roller support we have 1 reactions. Okay. And then now, if we divide the beam into, if we take a section at this point, if we take a section and divide the beam into 2 parts. Okay. Now, this is the one part and this is another part. Okay. Now, what is the free body diagram of first part? Free body diagram of first part will be this, and we have external loading on this, and then in addition to that we have an axial force, this, and then we have shear force, and then we have moment, right. And what is the free body diagram of the second part? External loading, and in addition to that we have internal forces, this, and then shear stress like this, and then moment like this. Okay. If it is V, it is F, it is minus V, it is V, it is F, and it is M, and this is M. So, what this M, V and F, if we define a field like this, F, V and M, what essentially they mean? F, V and M, it means that if we have two, this is part 1 and this is part 2, then these 2 parts, if we divide the entire structure into 2 parts, part 1 and part 2, these two structure interact with each other through these internal forces, okay, or through this field, they interact with each other. Now, when they interact with each other, when I say the body is in equilibrium, every point in the body is in equilibrium, so is this point as well. So, in order to maintain the equilibrium, this force and this force should be opposite direction, this force, the shear force and shear force at this plane should be in opposite direction, equal and opposite, and same is for bending moment. So, therefore, the equilibrium is maintained. So, these two objects interact with each other through this field, right. Now, similarly, if we take any three-dimensional object and if we cut it, then these two objects should interact with each other through some forces and couple, right, on this plane. Okay. Now, let us see that. So, let us take a small point here, okay, any small point, and then divide this entire object, entire three-dimensional object into two parts, being this as the common plane. Okay. Now, suppose this plane is S, this plane is S. Okay. Now, let us divide it into two parts, this is two part. So, this plane is S, this is S. Okay. Now, this is important. When we say a plane is defined by a vector which is normal to this plane, which is called normal vector. For instance, if this is a plane, this plane is defined by a vector called n. This is the normal vector. This is defined the same as this n normal vector. For instance, if we have, say, this is one plane, this is one plane, this is defined by a normal like this. Okay. So, if we know this, if we do know this normal n, then this n define this plane. Similarly, if we change the plane, if we have another different plane, suppose this is the plane, then a different normal vector defines this plane. Okay. So, at what is the cutting plane, that plane is defined by this normal vector. Okay. Now, so at any point, though the point we can, keeping the point same, we can have infinite number of points. Okay. So, in this case, two things are important: at what point we are at what point, and along the point what plane we have taken into account. If we change the plane, then at the same point we can have different the traction that we are going to define, we can have different traction at the same plane, at the same point, if we change the plane. So, two things are very important. One is what is the point at which you are calculating the traction, and the second thing is what is the plane you are considering. The plane has to pass through the point, but again there are many planes can be considered passing through the point, but which particular plane we are considering, that is important, and that is defined by this normal vector n. Okay. Now, consider a small area, say a small area on this around this point, consider a small area and consider small area. Suppose this area is delta A, this is delta A, a finite area, small area delta A. Okay. Now, when these two will interact on this surface, we have a force like the previous one, we have a distributed forces and couple through which these two body can interact with each other, right. Suppose they are this is suppose F, this is F, delta F, and similarly this is delta F, this is delta F. Okay. Now, remember one thing, if it is delta F force and this should be in opposite direction, so it is minus delta F, but we are already showing this is in opposite direction, that is why the minus sign is not written here. Okay. Now, similarly, we can have a couple as well. Suppose that couple is or use same. Suppose that couple is at this point is delta M. delta m. Similarly, we can have couple at this point is delta m. Delta m. Okay. Now, this is very important here. What our assumption is, now these two object number 1 and object number 2, the part 1 and part 2. Okay. Now, part 1 and part 2 will interact with each other through delta f and delta m, which is defined on a small area surrounding this point at this point, consider at this point, but a finite area delta a. Okay. Now, what happens that when delta, now you, as you remember the definition of stress, we defined the definition of stress was force by area, but that was not the complete definition of stress. The definition of stress is force by area with limit area tends to 0. That was the definition of stress, right? And that definition you studied in your class 2 as well. So, now in order to define stress, we need to consider an area which is very small. Okay. Now, when delta A tends to 0, when this delta A tends to 0, this delta m, this couple, the surface couple, this also vanishes. Okay. So, now when delta A tends to 0, then this couple vanishes. So, then the interaction between these two object or the two part can be defined only through delta f, right. So, if we define a quantity, so T n, for instance T like this, which is limit delta A tends to 0, delta f by delta A. Let us define a quantity like this, which is essentially in dimension wise same as stress, force by area with area tends to 0. Now, this point is very important. This is, we said that this interaction only through delta f. This is possible when delta A tends to 0, right. Then we can have this, the effect of the couple, the M is called surface couple, and this one is surface force, this is surface force. Okay. Now, because of this surface couple, we can also have stress which is called couple stress. Okay. Now, in this case, when delta A tends to 0, as delta m vanishes, the couple stress also vanishes. So, then in that case, the interaction between these two body is only through delta f. Now, if we define a stress like quantity, say T, as delta f by delta A with the limit delta A tends to 0, then use n here just to say that these forces and area on a plane which is normal to n, which is defined by normal vector n. Then this T n is called traction or traction vector. Because force is a vector. Okay. Now, but at this point, one thing you can note it, but there are some continuum theory, say advanced solid mechanics, so there are continuum theory which do take into account this effect of couple stress, but within the classical continuum mechanics and also in the context of this subject, these we do not consider. Okay. Okay. Now, that is essentially causes stress principle is. Now, so this is traction vector. So, traction vector is essentially, traction is dimension wise, it is also a force, but that this is defined, force can be the stress. When we wrote in a tensor form, stress is always at a point which has a which can be written, which has stress components in 3 dimensions. But when we talk about traction, traction just not a point. Traction also another important addition to the definition is at which plane we are calculating the traction. Okay, and when traction is equal to, this is traction. Okay. Okay. Now, once we have understood what is traction, let us try to find out, let us see how to determine traction. You see, suppose at this point, suppose this is the point of consideration, at this point we have a stress sigma, right, sigma. But then traction is dimension wise it is a stress, but it is not a tensor, it is not a second order tensor. Okay, it is a first order tensor or a vector. Okay, because this stress is projected, this stress at a point is projected on this plane, and when we project it, that projection gives you traction. So, traction is a stress like quantity, it is a vector. Okay, now maybe when we compute this traction, when we find out the relation between traction and the stress tensor at this point, probably things will be clear. So, this is the traction. So, traction is through which different parts of the body interact with each other. Now, let us move on and then see how to determine traction. Okay, but before that, let us simplify our notation. You see, now onwards, instead of writing sigma xs, sigma xy and so on, we will use sigma 1 sigma 1 2, which will be easier to write. So, sigma xx is this. So, this representation of stress now become this, and this stress tensor is this, but the way it is represented they remain same. For instance, sigma 2 2 is the sigma, it is the stress component on a plane which is defined, which is normal to direction 1, and then the direction of the stress is 2, and that definition remains same. Okay. Now, consider so this is our stress tensor at a given point. Okay, and x1, x2, x3 are the coordinate axes. Now, consider E1, E2, E3 are the basis vector in x1, x2 and x3 directions. Okay, you look at that this T, if we defined say T1 or TE1 also, you can say TE1. TE1 is essentially what? TE1 we have sigma 1 1, sigma 1 2 and sigma 1 3, right. So, TE1 is essentially your sigma 1 1, sigma 1 1, which is in E1 direction, and then plus sigma 1 2, which is in E2 direction, and then plus sigma 1 3, which is in E3 direction, right. Similarly, TE2 we can write TE2, which is sigma 2 1 E1 direction E1 plus sigma 2 2 E2 plus sigma 2 3 E3. So, if it is the plane, it is the plane. So, essentially your T1 is on this plane, this is your TE1, okay, and then we have T2 on this plane, which is TE2, and then T3 will be on this plane, which is TE3. Okay. So, component of TE1 essentially are written in terms of these basis vector as this. Okay. Now, similarly, we have, if we write TE3, the components will be E3 in x direction, in one direction, x1 direction is a sigma 3 1. So, this is sigma 3 1 E1, this is how we represent, and then sigma 2 3 E2, and then plus sigma 3 3 E3. Okay. Now, if I have to write this in initial form, then TEI ei could be I varies from 1 to 3. So, this will be equal to your sigma I j E j. This is very important definition. Okay. So, this gives you traction, on this plane, this gives you traction on plane defined by E2, and this gives you traction on plane defined by E3. So, TE1, TE2 and TE3 are the traction on different planes which are defined by E1, E2, E3 respectively. Okay. Now, this directly comes from the representation of stress, right. So, this definition, this expression we will be using shortly, this initial notation. Now, let us move on. Take this this 3-dimensional, that is a small volume element that we considered, and we also know that this is your this is E1, this is E1 and this is E3 and this is E2, right. And we also know that traction on this plane is T1, traction on this plane is T2 and traction on this plane is T3. That is now we define. Now, let us now, in order to compute traction, now what we want to know is, we know what is T1, T2, T3. We know that TEI is equal to sigma I j E j. That is, we know, that comes directly from the state of stress at this point. Okay. Now, what we are interested now is, suppose consider a plane, say consider a plane like this, cut a plane like this, this is the plane. Okay. And suppose this plane is defined, any plane is defined by a unit normal. Suppose this plane is defined by a normal n, okay, normal vector n. Now, at a point, this is very small volume. So, this area is also small. Now, what we are interested now is, we are interested to find out what is T n. That is our objective. But what information we have? We have this information. So, from this, how to determine this? So, we know traction on 3 planes, and with that information, how to find out traction on an AB arbitrary plane. Okay. Now, let us see that. Okay. Now, this is the this is the plane we consider. Now, suppose this area is dA1. dA1 is the area which is in x2 x3 plane, and then this area is dA2 which is an x1 x3 plane, means this plane is normal to E2 x2 direction, and dE3 is the plane which is in x1 x2 direction. And then the area which is, this is the area, this is dA. Okay. Now, what we have is, now on this plane, suppose this plane is now normal is n, and we want to calculate what is the traction on this plane. Okay. Suppose this is T n, okay, traction on this plane. But what information now we have is, we have this information. If we see on this plane, we know T1, on this plane we know TE2, and on this plane we know TE3. Okay. Just now we wrote. Okay. And Tij is equal to, this Tei is equal to sigma Ij Ej, that is we know. Okay. Okay. Now, if it is in equilibrium, then what are the forces we have? Now we have these three forces, these three stresses which can be converted into forces, these three T1, T2, T3 on three mutually perpendicular plane, and then on this inclined plane we have this traction N. Now, then if we have to write the equilibrium condition, then equilibrium condition says that total force on this plane will be traction into traction vector on this plane into dA, which is the area of this. Now, remember we are not writing delta A anymore, because we have assumed this area is very small, that is why. So, that is why the differential form we are writing it. So, dA1 that should be equal to it's minus TE1 into dA1 minus TE2 into dA2. It is just simple force balance, it should be minus, then minus TE3 into dA3, that should be equal to 0. That is for static equilibrium condition. Okay. Say this is equation number 1. This is equation number 1. Now, let us find out that if we have any relation between dA1, dA2, dA3 and dA? Yes, we do have. Let us see, if you remember, then you studied dot product between two vectors, inner product between two vectors. Suppose you have a vector, we have a vector say u here and another vector say v, So, if we take inner product u dot v is essentially gives you the projection of one onto the another. Okay. So, when we talk about the projection, then what happens? Your dimension reduces. So, vector, when we take the dot product between two vector, which is the projection of one vector onto the another. So, essentially it becomes a scalar. So, similarly, if we write write dot product between say n dot product, use different, okay, dot product between n and E1, they all are vectors. So, I am not explicitly writing the vector NE1 is essentially what? NE1 is essentially the projection of n on E1. Now, if we multiply this by dA1, dA, the area of this, then this essentially gives you projection of this area on a plane which is defined by E1, which is essentially dA1. So, dA1 is essentially projection of dA on this plane, which is obtained by just simply taking the dot product. So, this is equal to then dA1. Okay. Now, suppose N1 is equal to, N1 is a vector which is N1, N2 and N3. Okay. And then E1, in this case E1 is what? E1 is equal to say 1 0 0, and then E2 is equal to, you can check 0 1 0, and E3 is equal to 0 0 1. So, N1 dot E1 gives me, if you take dot product between this and this gives you dA1 N1 into dA. Okay. Now, similarly, dA2 can be obtained as n taking dot product E2 into dA, which gives you N2 dA, and then dA3 similarly n into E3 is equal to N3 dA. Now, with this, if I substitute this dA1, dA2, dA3 in this expression, what we get is essentially this. If we substitute this, then we can write it, okay, we can write it here. So, from this we get is we get Tn then equal to Te1 N1 plus Te2 N2 plus Te3 N3. You check. This is from equation number 1 to equation number 2. Now, can we write this in initial form? If we write this in initial form, then what we get is Te T n is equal to, then from this what we get is T n is equal to T E I into N I. Okay. So, this is, we are almost done. Okay. So, we have two thing here. One is T n is equal to, T n is written in terms of T I, which is T I N I. Then we have T I, which is written in terms of sigma I j, this. So, if I take this is equation number 3 and this is equation number 4, if we substitute this thing in this expression, what we get is this T n is equal to sigma I j n I E j. This is very important expression. You see, so if we know sigma I j, which is defined with respect to coordinate system, which is that coordinate system is defined with respect to the basis vector E1, E2, E3, Ej, and then if we take a plane, any arbitrary plane which is defined by vector n I, which is a normal vector n, then traction on this plane can be obtained by this. Okay. Now, so traction is, now let us write it here. So, traction is written as T n is written at sigma I j and then n I into E j. Okay. That is what just now we wrote. Now, traction T n is a vector. So, if T n is equal to if T n is equal to T 1, T 2, T 3, then T j can be written as T j, the jth component of this can be written as sigma I j n I. This is the jth component. So, this is the entire vector, initial notation in the vector and the initial notation of the each component of the vector. Now, if I have to write in matrix form, then we can write that T is equal to you see what is essentially this if you remember the dot product, this inner product, this is essentially the inner product between sigma and n. So, it is inner product between sigma and n. Okay. This is important. Now, you see, if we just now as I said that the physical interpretation of inner product is essentially the projection of one onto the other. So, if we take sigma is the state of stress at a point, and if we have a plane which is defined by n, then if you take sigma dot n, the inner product between sigma and n, essentially what it gives you projection of sigma on that plane. Okay. So, whenever we have a projection, a dimension decreases. So, sigma is a second order tensor. When we have inner product with a first order tensor, the resultant is a first order tensor, the traction, which is traction vector. Okay. Traction vector. So, this is traction vector. So, this is very important. This is how we can compute traction at a point. Okay. Now, with this, just one small thing before we close, we have stress at a point. This is our point. This is the point. This is the point, stress is defined as sigma at that point, and then we have a plane which is the area of this area, we have a plane which is defined by normal vector n, and then we take a small area dA, and then just now we discussed that traction is sigma dot n or it is sigma dot n. Now, then what this is traction which is sigma dot n. Now, this is essentially a vector. Now, if I take a dot product between this vector and n, if I take a dot product between Tn dot n, dot product between Tn and n, again dot product between two vector, inner product two vector is the projection of one onto the other. So, inner product between Tn and n gives you projection of Tn on n. Projection of Tn on n is equal to this n. So, which is the Tn not, please note one important thing, Tn not necessarily in the direction of n. Tn is acting on a plane at that particular point, but its direction could be anything. Its direction is not same as the normal direction n. So, if I take the dot product between these two, then we get the normal component of Tn, which is perpendicular to this plane, which is sigma n. So, sigma n, which is we can say the normal stress is essentially Tn dot n. Okay. Now, if I write in the initial form, this becomes that Tn is equal to sigma ij n sigma ij ni, and then the dot product become nj. So, sigma n is equal to this. Okay. So, this is the normal stress on this plane, Okay. Now, what is the another thing, what is the dimension of the sigma n? Dimension of the sigma n is dimension of Tn is a first order tensor, n is a first order tensor, inner product between two first order tensor, it gives you a scalar. So, dimension of sigma n is a scalar. So, it is just the normal stress on this plane. Okay. So, if I have to get the shear stress on this plane, suppose this is the shear stress sigma s, this is normal sigma n, this is sigma s is the shear stress. So, sigma s will be, sigma x will be. So, if we use this Tn is the resultant force, Tn this is square minus sigma n square, this gives the normal stress on this. Okay. Now, this you can write in initial form. Okay. So, let us just briefly summarize what we have learned, what we have discussed today. We have discussed what is traction, and then physically try to understand what is the meaning of traction, and then if we know the stress at a point, how the traction can be related, can be obtained from the stress of a point. And with that we have understood that traction is essentially, if you know the stress at a point and consider a plane passing through the point, then traction is essentially the projection of that stress onto that plane at that particular point. Okay. Now, and that traction is and since it is a projection of that stress, it can be obtained by the inner product between sigma and n. We also defined that once you know the traction on a plane, then the normal and shear component on that plane can be determined again using the projection of that traction. Okay. Another important thing here, please note that traction, whenever we call stress, it is stress at a point. If we identify the point, fix the point, the stress is defined at that point, can be represented at that point. But when we talk about traction, it is just not the fixing the point. On that point, which plane we are considering, that is also important, because at the same point we can have infinite number of planes, but if you have different plane, the traction on different plane will be different. Though the state of stress at that particular point is same, but since the planes are different, the projection of that stress on different planes will be different, and that is why traction will be different on different plane. Okay. So, we stop here today. Next class we discuss what is in the first three classes we discussed the different concept of stress, different representation and different projection of stress and what is the physical meaning of that projection. Next class we discuss what is strain, how when a material undergoes deformation, what are the possible modes of deformation, and from the deformation how to define strain and what are the different kinds of strain. Can we write the strain in a tensor form, the way we have expressed stress? Can we find out the symmetry in that tensor, the way we found out symmetry in stress tensor? Those things we will discuss in the next class. Okay. So, next class, thank you.